Hello everyone, my name is Al-Shatnawi. I'm working under supervision of Professor Amir Asif and Professor Agent N. Today I'm going to present my work on multiple pedestrian tracking system based on modified mask convolutional neural networks and enhanced particle filter for video surveillance. This work supported by Creative Dev and Brain Alliance in addition to IBM. Presentation overview will start by motivations, then we will discuss the problem statement, and then we will discuss our proposed multiple pedestrian detection component where we used the mask convolutional network with post-processing steps. This combination where we integrate the mask convolutional neural networks with post-processing step is a novel combinations. And then we will discuss our proposed pedestrian tracking algorithms with adaptive information-driven motion model. Some sample of output result, then we will have experimental results, and we end with conclusions. In terms of motivations, multiple pedestrian tracking system is considered as important for wide range of computer vision applications such as video surveillance, traffic safety, and support analysis, to name a few. In these applications, we have to be accurate and precise in terms of detecting and tracking pedestrians. Also, the most popular framework is track by detections, which divide the step of tracking pedestrians in two steps. First, we detect the pedestrians, then we track the pedestrians. So improving the performance of detection components leads to the improvement of overall tracking systems. In terms of problem statements, in literatures, most of multiple pedestrian detectors split the input video into independent frames, which leads to detect the pedestrians in each frame independently, without considering interframe relationship that exists between two consecutive frames. Also, most of the existing multiple pedestrian tracking algorithms that are based on a particle filters assume that the motion of the pedestrians most likely are piecewise linear and predictable. Therefore, they adapt the linear constant velocity motor to propagate the particles from the previous frame to the next frame. But in reality, the motion of some pedestrians is highly dynamic. What do you mean by that? Pedestrians, sometimes they stop while they are moving. Sometimes they move forward. Sometimes they move backward. Sometimes they turn in circles. So the movement of the pedestrians, they are not always linear, and they are not always moving with constant velocity. Sometimes the pedestrian is moving forward with full speed, then stop for a period of time, then again move slowly in the second part of the video. Some facts and observations about multi-pedestrian detectors. If you were able to detect the pedestrians at a certain frame time t-1 with high confidence about these detections, let's say a probability about detection of the pedestrians with high probability, it most likely these pedestrians will be present on the next frame at time t. Also, we should keep in mind that the same pedestrians might have different appearance due to the background changes and contrast and other factors that exist on the live video surveillance. So detecting the pedestrians at frame t-1 with high confidence, most likely these pedestrians will exist at time t, given that whenever you are taking a video, most likely you are taking it at 30 frames per second or 20 frames per second. So within 30 frames per second, most likely if you see the pedestrians, it will stay for this period of time. In this slide, we will present the mask convolutional neural networks detectors for the pedestrians. And these detectors, it train on the COCO databases. We try to run this standards or mass convolutional neural networks to detect the pedestrians. And we present here on this slide three consecutive frames from PITS 2009 view 1. The first frame is 311. As you can see, the both pedestrians inside the red circles, they are correctly detected with high confidence and as two independent pedestrians. But as we move to the next frame, 312, the mass convolutional neural networks was not able to distinguish that these are two independent pedestrians. They end up with the same pedestrians. They detect only single one bounding box. So based on our observation, this is a mistake. This is increase the or showing how the mass convolutional networks fail. Back to the observation that if you detect the pedestrians in the previous frame with high confidence, most likely this pedestrian will stay with you, and that is the case. But actually, the detector was failed to detect the pedestrians. If we move to the next frame, we can see the mass convolutional now again was able to detect the pedestrians with high confidence. So the frame 312 represents a failure for the mass convolutional neural network to detect the pedestrians. Today, we will discuss how the fast processing step that we propose with combination with mass convolutional network can improve these detections and get rid of these mistakes. This is another example from BITS 2009, view number 8. And again, we are taking three consecutive frames, 685 and 686 and 687. As we can see on 685, the two pedestrians inside the red circle, they are detected completely isolated with high confidence. Now, on the next frame, there was a complete inclusion of the pedestrians end up by missing one of these pedestrians. If we see the pedestrians on the previous frame with high confidence, most likely this pedestrian exists again on the next frame with high confidence. But unfortunately, the mass convolutional neural networks was failed to do this. If you get to the next frame, we see that the mass convolutional networks was able again to detect the two pedestrians disjoint. And this gives us an indications about what we said earlier. The mass convolutional neural network treat each frame independent from each other. We're going to see today how our proposed post-processing steps will try to improve the original detections from the mass convolutional neural networks. These are also some random mistakes from mass convolutional neural networks. As you can see on these figures, the cone is detected as a pedestrian, which is actually not a pedestrian. It's a solid object on the pictures. And these are two examples from different videos. As you can see, the cone from the other side is also detected as a pedestrian, and the camera is detected as a pedestrian. Here is very obvious mistakes from the mass convolutional neural networks, where the shadow of the pedestrians is detected as a true positive. Back to the assumption that most of the multiple pedestrian tracking build based on particle filter assume that the motion of the pedestrian is linear and can be assumed as a use linear constant velocity model to track them. Here is an example about the motion of the pedestrians taken from frame 361. As we can see, the pedestrians are moving, the trajectory of the pedestrians is completely random, it's not linear. They move backward and some of them they move in circles. Also, if we look at the right side, we see the same video sequence but are sampled at frame 793, and where the trajectory of the pedestrians is moving on circles, especially the green one, is moving on circles, not on the linear. So it's very hard to model this trajectory using linear constant velocity model. Also, if we take sample from EDFL trace camera 1 at frame 1903, you can see the trajectory of the pedestrian is completely random. The same story is seen also at frame 3208 from the same video sequence. The trajectory is completely random. The persons are moving on circles in front of each other. It's very hard to model these motions as a linear motion and assume it's a linear motion. Doing so will end up with lowering the accuracy and also increase what we call the ID switch in terms of identity of the persons. Let us discuss just in details a little bit about multiple pedestrian tracking algorithm based on the particle filter when they adapt linear constant velocity model, what they are assuming. Due to the fact that the posterior probability is very hard to sample and there's no precise formula for that, these multiple pedestrian tracking algorithm based on the particle filter, they use linear constant velocity model. They assume the transition probability as the proposal distribution functions. So they sample from the transition probability. So they move the particle from the previous frame to the next frame using the transition probability. There's no involvement for the observation or the new detection on the movement of the particle. The only involvement for this observation on the reweighting the particles. It's a problem of the existing algorithms. We will try to use the adaptive motion models to help in moving the particles from the previous frame to the next frame using the adaptive motion model we propose here. This is an example from sample result from the multiple pedestrian tracking component using linear constant velocity models. As we can see in the figure A and P, the tracker was failed to keep the ID of the person. The ID initially was assigned on the frame 32 as 3 for the pedestrian inside the green box. But once we are going to the next frame at frame 33, the ID is switched from 3 to 4. Even there is no big difference in the appearance of the person. This indicates the movement of the particle using linear constant velocity failed to adapt the motion of the pedestrians. The same story on the vectors C and D, where it's taken from the same video sequence from frame 189 to frame 190, where the pedestrians was initially labeled as a 20, given an ID 20, but after that is given an ID 23. So moving the particle using the transition probability failed to adapt the motion of the pedestrians. This is a clear also failure for the multiple pedestrian detectors using linear constant velocity models, where the pedestrian is moving with forward motions, and we see on a figure A we give ID 6 to the pedestrians, but in figure P we give 7, and these are two consecutive frames from frame 71 to frame 72. And on C and D also the ID switched from 7 to 8. Not only that, but at E, where after one more frames at frame 79, the ID is switched from 8 to 9. So the linear constant velocity models to propagate the particle from next frame to the next frame, ignoring the fact of observation, lead to higher ID switches. We will try today, we'll propose a adaptive motion models that can help to lower this ID switches and increase the accuracy. First, we will discuss our proposed multiple pedestrian detectors using the mass convolutional neural networks with bus processing step. We call it modified mass convolutional neural networks. First, we have the video sequence. We run the mass convolutional neural networks. We generate the pedestrian detectors with confidence and with bounding box, and the first mass processing steps remove the outlier detections. How we detect the outlier detections? Using the distribution of the area of the bounding box. By calculating the area multiplying width with height, we can calculate the area distributions. and we remove the outliers. All the samples that within the mean plus 2 times the standard deviations, if it's greater than this amount, will be removed. If less than mu minus 2 times sigma, which is mu is the mean and sigma is the standard deviations, will be removed too. This is the first step. Second step is propagate the high confidence pedestrian detection from the previous frame. So given the fact that whenever you receive a detection, you're going to say if you have the detections that is greater than the first quarters, you're going to say this is a true positive. Now, what about the one that is detected with very low confidence? Are you going to get rid of them? Or you're going to look at the previous frame, the ones that are greater than the third quarters, you're going to include them in your set, and you're going to get rid from the ones that is not seen at all. That will generate the final pedestrian detections. So once we modify the mask convolutional neural networks. Once we generate the pedestrian detections, we try to do the bash processing step. The first one is to get rid of outliers. The second step to propagate the high confidence pedestrian detection from the previous frame to generate the final pedestrian detection at time t. Having these detections, we're going to feed it to our proposed algorithms for the tracking algorithms. Here we are having the previous trackers and we receive a new detections. We try to match between them by doing the data associations. And once we have a true match, we're going to update the particle filters with using the adaptive motion models. So we're going to keep some set of the particle that propagate, and we're going to use the new observations to generate a new set of particles. We add this set to the original set and resample again from the new set. So we're not only using the observation to reweight the particle as the other people do, but also we use the observation in the moving the particle from the previous frame to new frame. So once the particle is moved using the transitional probability, we generate a new particle clouds using the new observations that match with the trackers. And now we have a new set of particles cloud. And this new set of particle clouds will be resampled again to generate a new robust particle filter that can track pedestrians. Some sample from the output results. Here is the original examples where we saw the failure of the mask convolutional networks. Now, using the past processing steps, we are able to recover the pedestrians. So we remove the bounding box and we propagate the high confidence detection from the previous frames. Also, here is we have the inclusion scenario where the original mask convolution failed to detect the pedestrians. As we can see, now we propagate the pedestrians with high confidence from the previous frame to the next frame. These sample results from the tracking algorithms. These cases we saw it in the previous slides as a failure for linear constant velocity models because they are failed to propagate the particle correctly from the previous frame to the correct frame. Now, using our adaptive information-driven motion models, we were able to use the observations on the propagation also, not only for reweighting, but also to propagate the particles. Here we see the pink particle cloud, which is the new set of particles generated based on the observations. And we were able to keep the ID of the pedestrians. So in A and P, the pedestrians ID stay the same. Also, this scenario where is the original multiple pedestrian tracking using linear constant velocity model was failed. to keep the ID of the person. Using our proposed adaptive information driven motion model with the particle filters, we are able to keep the ID of the persons for all the consecutive frame. Experimental results, we compare our multiple pedestrian detectors with original mass convolutional notebooks. So we combined the mass convolutional notebook with the fast processing step. This was a novel contribution, and we increased the accuracy from 68 to 73, and we increased also the precision from 77 to 81, almost 82. In terms of the tracking accuracy and performance, we are able to implement our multiple pedestrian trackers using adaptive information driven, and we compare it with other two algorithms, state-of-art algorithms. We improve the accuracy and we improve the precisions. As we can see also, we lower the ID switches compared to others. As a conclusions, in this work, we have presented a robust approach for multiple pedestrian tracking system, enhancing the tracking accuracy and precision, as well as reducing the number of ID switches. And our proposed system use the track by detection approach. We have detection component and we have tracking component. We improve the track detection components, lead to improve the detection tracking component, but also we improve the tracking component using adaptive information. The result shown that using the fast processing step improve the detection result for the mass convolutional neural